In our last exciting episode, we had gotten down to here. I'd had you working on problem number 4, and that was about where we ran out of time. So now you've had all the time you want to work on it, and it's time for me to run through it and answer any questions. About like that. Okay, so the 3 lowest resonant frequencies. The lowest possible frequency would correspond to the longest possible wavelength. One support there. Got the other support over here. The rules of the game are that you have to have a node at a point where the clothesline can't move, because a node means a point of 0 vibration, or at least minimum vibration. To have the longest possible wavelength, don't put any other nodes in between. So the lowest frequency would mean when the thing vibrates with this pattern here. The wavelength of a standing wave is twice the distance between nodes. Well, it says in the question that the length of the clothesline is 3 meters. So in this case, that's the distance between nodes. So when it's vibrating in this particular pattern, when it's vibrating with this resonant frequency, that's the wavelength. I'll call the frequency F1, as in the first resonant frequency. Speed V has nothing to do with the frequency you're shaking it at, so that doesn't get a subscript, but F1 corresponds to this first wavelength. We're told in the question that the speed is 12 meters per second. You divide that by the 6 meters. Incidentally, maybe I should mention that when you do the lab for this particular unit, it's like most of the labs we do, there's going to be some theoretical prediction, which you then have to compare to what you actually observe. Well, the calculations that you do to make that theoretical prediction are going to be extremely similar to this example here. So you might want to have this in front of you when you're doing the lab. Maybe keep that in mind. The next lowest frequency would go with the next longest wavelength.
Scholastic Bowl to academic advisement, please. Scholastic Bowl, academic advisement.
So once again, there's the poles that are supporting this clothesline. And once again, you have to have a node at each end to have the next longest possible wavelength. Put just one node in between the ones that are required. So if the whole thing is 3 meters. And if you take 3 meters and divide it into 2 equal pieces, each of those is 1.5 meters. So this time our node to node distance is 1.5 meters. Once you have figured that out, the rest is just a repeat of what I did with the first frequency. Two times 1.5 would be 3. And then speed over wavelength to get the frequency. For the third one, pattern of vibration with the next longest wavelength after that. First frequency, it vibrated with 1 node to node segment. Second frequency, it vibrates with 2 node to node segments. Probably no surprise that for the third frequency, the mode of vibration would have 3 node to node segments. If you take 3 meters and divide it into 3 equal pieces, each of those pieces is 1 meter long. So as always, the wavelength is twice the distance from one node to the next. Speed is still 12 meters per second. Divide that by 2 meters. You've got 6 hertz. And at this point, you can probably spot the pattern. If the question had asked for more, the fourth frequency would be 8 hertz. The one after that is 10, and then 12. And all of the resonant frequencies are whole number multiples of the first one. So when you go to do the calculations for the lab, I was saying a minute ago, you'll need to do this, but once you've seen the pattern, there's a shortcut you can do for the rest of it. Instead of doing this and this, once you've got the 2 hertz, you can just say times 2 gives you 4, times 3 gives you 6, and that'll give you the answers a little quicker and easier. So in example number 4 here, the resonant frequencies were 2, 4, 6, 8, 10, 12, 14, and onward to infinity. Although with the really high frequencies, you wouldn't really be able to set those up on the string. The assumption that the string is completely flexible would kind of break down if you started shaking it at, hundreds or thousands of hertz. But this type of arrangement is called a harmonic sequence. all the resonant frequencies are integer multiples of the first one. Not all vibrating systems have resonant frequencies that fit this harmonic pattern. If you hit a garbage can lid, I don't know exactly what the resonant frequencies are, but just to make up an example, maybe the first resonant frequency is 100 hertz, and then maybe the second one is 251, and then maybe the third one is 287, and then the next one is 512, and it can be a lot more complicated. But any resonating system used in music has this harmonic pattern, because like if you hit a garbage can lid, you don't really get a sound with a definite pitch to it. When those frequencies blend together, you just get sort of a thud. And vibrating strings have this harmonic pattern. A vibrating column of air, like you'd have in an organ pipe or some other wind instrument, a horn or a clarinet, they have this harmonic pattern. The frequencies fit together in a way that gives you a sound with a definite pitch. So, speaking of musical instruments, let's say, and we're down to around this point on the page here now, just above problem 5. Let's say you have a string in a piano, and when you press one of the keys, there's a little felt hammer inside of there that strikes the string and makes it vibrate. So when you do the lab that goes with this, you're going to have hold of basically the same kind of system as a piano string, just much heavier, so the waves go a lot slower. But you're shaking it with like this clothesline in this example. You got your hand on there, you're shaking it with 2 hertz, and then here you shake your hand faster and you make it go at 4 hertz. So you shake it at 2 hertz, it excites this mode. But if you shake it at 4 hertz, it excites that mode. But if you just strike something with a hammer, that doesn't really have any particular frequency to it. How does the string know whether it should drop into this mode or that one or one of the higher ones? And the answer is it doesn't. You set them all up at the same time, okay? You get the string vibrating like this, with this superposed on top of it, with that superposed on top of them, and so on and so on. And as the string vibrates back and forth with this combination of frequencies on it, the surrounding air, I'm oversimplifying a little bit, a piano has a soundboard, but well, let's not get into that. As the string goes back and forth with this combination of frequencies, the surrounding air gets dragged back and forth with the same combination of frequencies. And so the vibration that reaches your ears has this combination of frequencies. Most of the sounds that you hear as you go around, living your life, most of the sounds you hear are not just a single frequency. They are multiple frequencies mixed together. And if those frequencies fit into this harmonic pattern, then it's a musical sound, a sound with a definite pitch. If it's a sound like somebody pouring sand on the floor, then it's just noise. You don't have frequencies. Actually, pouring sand on the floor, you'd have kind of a continuous spectrum with all sorts of different frequencies mixed together. What note you hear, assuming it's a sound with a definite pitch, what note you hear is determined by the lowest of the frequencies, the so-called fundamental frequency, the one that I called F1 in this example. The higher harmonics are often called overtones. Okay, so little bit of terminology. F1, the fundamental frequency, is also known as the first harmonic. F2, which is second harmonic, is 2 times the fundamental. Third harmonic is 3 times the fundamental, etc. So the fundamental frequency determines what note you have on a musical scale. As for all those overtones, harmonic number 2 through infinity, they determine the sound's quality. Okay. There, aside from loudness and pitch, there is some third characteristic that a sound has. Because well, especially if it was, you know, a woman sitting there and she and I are humming the same note, okay? We've got the same note, we're humming it at the same loudness, but she doesn't sound like me. And the difference is how much of each overtone you mix in, okay? Or it doesn't have to be 2 people singing. This is what makes a banjo sound different from a guitar, or, you know, a clarinet sound different from a horn, or, you know, same note, same loudness, but how much of each overtone has been mixed in. And that's how a synthesizer works. You know, if you want to have something sound like a clarinet, but you're just sitting at a keyboard doing it, well, they electronically produce all these different frequencies, and then you mix in the appropriate amount of each one to create the quality of the sound. Well, the other factor would be how the sound begins and tapers off at the end. That's kind of characteristic to different instruments also. But as far as just when in the middle, when you've got a sustained tone, it's how much of each overtone you mix in. Or another way of looking at it, how much of each overtone you mix in affects the waveform. So one person's voice, just to make something up, maybe you've got people's voices generally are not some simple little sine wave like you'd have in a math book. It's more complex than that. In this case, you've got this unit from here to here that repeats over and over again. As long as you've got some unit that repeats, you've got a sound with a well-defined pitch, okay? It's only when you get, you know, something that just jumps around at random, you've got noise. So somebody else humming the same sound, because this looks completely different if you're going A versus if you're going O versus if you're going E. But somebody else singing the same sound at the same loudness, same pitch, their voice maybe looks like that. And that's how much of each overtone you mix in creates different different patterns, different waveforms. If any of you goes far enough in something like electrical engineering, you'll look at something called Fourier analysis, but I probably shouldn't have said that in a course at this level. Anyhow, that's what this thing on the bottom is all about. The sound's quality corresponds to the relative prominence of its harmonics. So it's time for another example, right down at the bottom of the page. Find the speed of waves on the string, and that's part A. You have to refer back to an equation from that's a typographical error. You think I would have fixed that by now, because that was probably 6 or 8 years ago I changed that. Section 8 is alternating currents. That should say section 9. So just look back in your formula sheet from a week ago. There's a formula there for the speed of a wave. Number 5. From not too long ago, the speed of transverse waves on a string, square root F is the force in the string, the tension. Potentially confusing notation here. Capital F for force, little f for frequency. Mu is the linear mass density, the mass per unit length. The question tells us both the mass and the length of the string, but you have to adjust the units a little bit so that everything is consistent when you put it in the equation for V. Centimeters have to be changed to meters, grams have to be changed to kilograms. So 0.0013 of a kilogram is the mass of a string that's 0.7 of a meter long, which makes mu equal to 0.00186 of a kilogram per meter. So yeah, we've got let's see, the desired force is 150 newtons. A newton is based on kilograms, meters, and seconds. So this has to be kilograms and meters also to be consistent with that. Let's see, 0.00186, you divide, you take the square root, 284.2, close enough, 200, well, 3 significant figures, 284 meters per second. Yeah. So you would need to adjust, if that's the speed that's going to give you the correct pitch for the string, you'd have to adjust the tension to 150 newtons to give you that speed, and that's how you would tune the thing. Part B. What is the fundamental frequency? Fundamental is what determines what note this is. So the fundamental frequency is quite often the one you're interested in. And a string, when vibrating at its fundamental mode, moves back and forth with this pattern here. From there to there is 0.7 of a meter. Wavelength is twice the distance from node to node. So when a string is vibrating at its fundamental frequency, the wavelength is always going to be twice the length of the string. Now that we have the wavelength and then we have the speed from part A, you can get the frequency. And then part C, well, you could go through it the long way, the way that I did number 4, where, you know, for the second harmonic, the wavelength would be 0.7 meters. For the third one, you divide this by 3 and then multiply by 2. For the fourth one, you divide this by 4 and then multiply by, that'll give you the right answer. But once you've seen that the frequencies fall into this harmonic pattern, the quick way to find the overtones is just to say that F2 is 2 times F1, which would be 2 times 203 is 406. 3 times the fundamental gives you the third harmonic. Four times 203 gives you the fourth harmonic. And now it's time to turn the page. And looks like there's another example there to work on. Tell you what, why don't I just run through the rest of this, and then you can pick off 6, 7, and 8 all at once. I'll only have to pause it once that way. So, a little bit lower. Okay. A few words about wind instruments. Standing waves in a tube, standing sound waves, as opposed to transverse waves on a string resonating like you have on a string instrument. It's kind of a variation on the same idea. What you're going to do for the lab in this part is you'll have a tube about, I don't know, an inch across or something like that. You're going to hold a tuning fork over the top of it. And that makes sound waves go down into the tube. When it gets to the bottom, they reflect, just like, you know, sound reflecting off the side of a barn or something like that. And so you have the reflected sound coming back up the tube, while newer sound directly from the tuning fork is going down the tube, and they superpose and they form standing waves. The boundary conditions that have to be obeyed, kind of like the ones for a string. A fixed end on a string has to have a node because the string can't move there. A closed end on a tube, that little dot there is supposed to be a typical air molecule. This little squiggle, by the way, on the other side of the picture of the tube, that's supposed to look like I ripped off the other side of the page, because I don't care what the other end of the tube looks like. So I just imagine I just tore it off and took it away. But at this, remember, sound is a longitudinal wave. So if that dot is a typical air molecule, a sound wave is going to make it want to vibrate back and forth horizontally, but it can't because the end of the tube is in the way. So it's prevented from moving, just like a fixed end on a string is prevented from moving. And that forces a node to be at that point. Just as I think I mentioned the other day that a free end on a string would have an antinode on it. And in kind of the same way, an open end on a tube has an antinode. It's open to the atmosphere. There's no obstructions whatsoever. You get a maximum of vibration there. So this time, you know, with stringed instruments, you always have a fixed end. With wind instruments, sometimes you have a fixed end, sometimes you have an open end. You get things like a flute where it's open on both ends, okay, because you just, on the one end, you got that hole that you blow across, and at the other end, you know, the tube is open. Other instruments like a clarinet are open on one end and closed on the other. And in that case, you'd have to have, you know, clarinet is closed at the mouthpiece. I mean, there's a tiny little gap between the reed and the rest of the mouthpiece that opens and closes rapidly, but basically it's a closed end. So you have to have a node in a clarinet. You'd have to have a node up at the end by the mouthpiece and an antinode at the open end, which means on a tube like that, one that's closed on one end, in the fundamental mode of vibration, you'd have a quarter of a wavelength equal to the instrument's length, because node to antinode's a quarter of a wave. Something like a flute where it's open on both ends, you'd have an antinode at both ends. Antinode to antinode is half a wavelength, so the length of a flute would be half a wave. So having said that, the rest of it is all just kind of the same thing, you know, very similar to strings. And there's some questions here to kind of reinforce all of that. So you work on them and then I'll go over them. Okay, here we go with the rest of these sample problems. Number 6. Ought to work like that. Tells you the length of the string, tells you the note that you get when you pluck it. So first of all, what does that make the speed of the waves? Well, what note you get corresponds to the fundamental frequency. And when the thing vibrates in its fundamental mode, like this, the length of the most popular mistake here is a factor of 2. People use the length of the string for the wave length, but when it's vibrating in its fundamental mode, the length of the string is half a wavelength. So this thing is 56 centimeters, 0.56 of a meter. And wavelength is twice that. Once you know the wavelength, the frequency is given in the question, you can get the speed. 440A, 1.12, twice the length of the string, 493 meters per second, which is actually faster than the speed of sound. But remember, we're not talking about sound waves here. This is the speed of transverse waves moving back and forth on the string, okay? As the string vibrates back and forth, it makes the surrounding air vibrate and creates a sound wave with the same frequency. But what we're talking about here is the waves moving along the string, not sound waves. And they move at 493 meters per second. Part B. So then you decide you want to play a C instead of an A. Where should you put your finger? In other words, if it's a guitar, where does the fret belong for that particular note? Well, that's basically the same process, you just turn it around the other way. Starting from knowing the frequency, well, maybe I shouldn't say it's exactly the same process, but it's going to be the same equations. The speed of the waves is still going to be the same. Just putting your finger on the string does not significantly affect the tension, maybe a tiny bit. And it doesn't change the mass per unit length at all. And so basically you still got the same speed. So from knowing the speed and the frequency you want, you can figure out the wavelength that you want. And the length of the string should be half of that wavelength. So to write out the details, I'm playing the C. The wavelength is 0.942 of a meter. And then I'll make a little sketch of what's going on. That's supposed to be your finger right there, kind of pinching off the wire so that it vibrates back and forth like that. And we want to know this length L, the length of the vibrating part of the string. So 4.71 is the length you should have to get that note. The farther you move your finger, the shorter that vibrating length gets, which gives you shorter wavelength, which gets you a higher frequency. Well, rather than move the camera, I guess I might as well just erase that, because it's not like a class where to make sure everyone's had time to take it down. It's a recording, you can just pause it if I erase something too quickly. So number 7, fundamental frequency of a clarinet. Here's a simplified cross-sectional view of the clarinet. Now, of course, a real clarinet kind of flares out a little bit at the end, and the other end isn't quite that boxy and so on, but to a decent approximation, this is what you're dealing with. As it says just above the problem, at a closed end, you have to have a node. At an open end, you have to have an antinode. To get the lowest possible frequency, you want the longest possible wavelength, which means don't put any other nodes or antinodes in between. It says the clarinet is 0.6 of a meter long. So then looking at the little sketch, you can see that from node to antinode is 0.6 of a meter. So one of a couple of things that are a little different about this compared to a vibrating string is that the length of the instrument is 1/4 of a wave rather than 1/2 a wave. 4 times 0.6, 2.4 meters. And then calculate the frequency that goes with that. Now, unlike a stringed instrument, this time we're talking about a standing sound wave, okay? You've got sound waves echoing around inside that tube. So this time, V is the speed of sound. Assuming it's room temperature, 343 meters per second, divided by that 2.4 that I just came up with, 143 cycles per second. Another thing that's a little bit different from a vibrating string is to get the next resonant frequency. Turns out you do not just multiply by 2. Let's, instead of just assuming that, let's go back to the basic principles and calculate it the long way. So here's the tube again. You have to have a node at a closed end. And again, the dot is supposed to be a typical air molecule. It shows it not moving where there's a node. And it shows it jiggling around with a large amplitude where there's an antinode. So you have to have a node at a closed end. You have to have an antinode at the open end. The next simplest pattern, in other words, the next longest wavelength after this one, would be if something like this is going on. So now, if you take the 0.6 of a meter and divide it into 3 equal pieces, each of them is 0.2 of a meter. And this is 0.2 and this is 0.2. Wavelength is once again 4 times the distance from node to antinode. 4 times 0.2 is 0.8. And then frequency is speed over wavelength. V is still same old speed of sound, divided by 0.8. 429 hertz, which is not 2 times 143, it's 3 times. And the question doesn't ask for this, but if we kept on going, you'd find that the next pattern of nodes and antinodes gives you 5 times the fundamental frequency, and then the one after that is 7 times. This type of tube is incapable of producing the even harmonics, which, you know, going back to what I said a little while ago, how much of each harmonic you mix in is what determines the quality of a sound. So the fact that it's pretty much entirely the odd harmonics is what gives this type of instrument its characteristic sound. Clarinets, saxophones, and so on sound a little different than a flute, for example, which is open on both ends. The flute can produce both the odd and the even harmonics, which gives it a different sound. So I think that's everything that number 7 asked for. And then the last one is kind of a quick one where you just draw some pictures. I should probably move this over a little bit. Flute behaves like a cylindrical tube open at both ends. Flute 70 centimeters long is vibrating its fundamental mode. What's the sound's wavelength? So here's a diagram of what the fundamental mode of vibration looks like in a flute. And again, I'm kind of oversimplifying a little bit because, you know, actually the hole on, you know, the hole that you blow across on a flute is actually on the side, not on the end. And we're leaving out a few details here, but basically you've got an antinode at the open end here. You've got an antinode at the open end there. And every pair of antinodes has to have a node in between. So there's the fundamental pattern. This is 70 centimeters. Antinode to antinode is half a wavelength. So the wavelength here is twice the length of the instrument. Part B is kind of a rerun of number 7, really. Repeat for a tube that's closed on one end. That, once again, is this pattern with a node here, node at a closed end, antinode at an open end. Node to antinode is a quarter of a wavelength. So from an instrument the same length, you get a lower note when it's closed on one end. 4 times 70 is 280 centimeters. Twice the wavelength would give you half the frequency, it would be an octave lower. And of course, the way you play one of these things, whether it's a flute or a clarinet or any, well, one way or another, you have to change the effective length of the instrument. Now, the way you do it with flutes and clarinets is you open up a hole on the side, okay? If you want a higher note, you open up one of those side holes, and now, you know, it's a big enough hole so that it's basically open to the atmosphere. Your antinode is there. If you shorten that node to antinode distance, that gives you a shorter wavelength, which gives you a higher pitch. Other wind instruments, instead of opening up holes, they change the effective length of it in other ways. For example, a trombone has a slide in it. You slide the thing out and it makes the tube longer, and you change node, you know, change the wavelength that way. Then with a trumpet, you've got valves on it that switch it from a tube that's one length to a tube that's a different length. But one way or another, you change this. If it's an open tube, you change node to antinode if it's a closed tube. And that's how you get different notes out of the thing. Or at least it's part of the story. Main thing. Looks like that's the end of section 10.